in those topics. So this morning's webinar is going to be on irrigation. I do hear somebody clicking on keys, so if you're not muted, if you can mute, that would help us out here. All right, so today we're going to talk about irrigation and energy efficiency. So in Wisconsin, most states are somewhat similar. I didn't go and get all the data for all the states, but in Wisconsin we have about 400,000 acres irrigated lands, and of that about 89% is center pivot irrigation. Center pivot is by far the workhorse of the industry and the biggest component of that. They can be run at a range of pressures. In this case, from the 2007 census, indicates that in Wisconsin anyway, 32% are high pressure, 52% are medium pressure, and about 15% are low pressure. That's one of the energy saving things we can do is by lowering the pressure, and we'll talk more about what the effects of that are. We also have some solid set sprinkler irrigation and some traveling gun irrigation here in Wisconsin as well. But those are much smaller. So why do we irrigate? Basically, it's to reduce risk. In many cases, it's so we can get a crop off of land that where we don't have adequate rainfall. Although a high percentage of fruits and vegetables are irrigated, even in areas where they're on a yearly basis there is adequate rainfall. In the U.S., about 80% of the water use is for irrigation, and so that's a sizable chunk, and we only irrigate about 16% of our cropland. So you can see there's a sizable chunk of water used. So what are the concerns? One of the reasons for basically becoming more efficient either with water use or energy is because we have reducing water tables in some areas of the country, even sometimes in places where we have adequate water supplies. We have drying up of lakes and streams. We have that problem here in Wisconsin on a dry year. We have some streams and lakes that levels be very low on. And because of these issues, we have increasing regulations. So how much, oh, my slide didn't quite work here. It's going to be a question. Anyway, how much water does it take to put an inch of water on? About 30,000 gallons of water. A lot of people don't quite understand the amount of water needed to water an acre. Last summer with the drought, I got calls from people wanting to irrigate 10 acres of sweet corn off of a old-fashioned windmill, and it just they don't have a concept of how much water it takes to water things. So if you're going to truck that, it would take 4 to 5 semi-loads per acre to put an inch of water on. So a typical water application is maybe 6/10, so you have 2 to 3 semi-loads of water if you want to irrigate 1 acre of land. So how much water do we need? It all relates to the amount of water that the plants use, and it's called evapotranspiration. And then the amount of water also depends on whether we're trying to do full irrigation or deficit irrigation. Deficit irrigation is where we supply the plants enough to grow some, but they still may be stressed slightly. So in Wisconsin, the amount of water the ET, typical ET is about 0.3 for some of the hottest days during the summer, and that will require about 7 gallons per minute per acre of land irrigated to meet that requirement. And that's assuming about a 10% loss from applying it. If we get down to an arid area like Kansas and Nebraska, they're probably in the neighborhood of 10 gallons a minute because their ETs on a hot summer day can be 0.45, and and because of that, because of the arid or dry weather, they have higher irrigation losses. I'm slating here about 15%. So you'd be a little over a ½ inch of water a day. So substantially more irrigation required. So what are the types of efficiency? You know, I'm an engineer, so we like to look at efficiency of all different types. So here's some of them that have been used throughout the years. One is water conveyance efficiency. So that's the amount of hang on a minute, I'm going to get a pointer here. I got to change colors. So it's the amount of water or percentage of water that reaches the field. In most piping systems, it better be 100%. This was actually came about mostly because of open channel water supplies out west where they use snow melt. We have a lot of open channels. The other would be water application efficiency. So that's the amount of water delivered to the field, not necessarily worried about how evenly it's spread. And then we have irrigation efficiency, which accounts for other beneficial uses. Here in Wisconsin, we do a lot of frost protection. Actually, with cranberries, we do cooling. Some people do chemigation. And then in some areas where you have lots of irrigation, you have to do some salt leaching at times. Another way is to look at the water distribution efficiency. So that's the degree of uniformity of the water infiltrating into the soil. And that's pretty tough to measure, but that's another measurement. The one we're going to talk about later on in this presentation is distribution efficiency, or sometimes it's called the coefficient of uniformity. And that's how evenly the water is spread on the field or applied to the surface of the soil, not necessarily how much goes in, because the slope of the field or what's on it may dictate how that water travels once it reaches the soil surface, whether it soaks right in or moves. So here's an example of conveyance efficiency, or lack thereof. So we got a hole or a area on the pipe where it's leaking. Application efficiency, basically this is the amount of water that reaches the edge of the field. So it's affected a little bit by the losses in the field, but this is a formula for putting it together. So here's an example on the bottom. If we know the gallons of water per minute, this is a conversion factor, and we know the hours, the acres. We can get we deliver to the field 0.62 inches, but if our actual application is ½ inch, then we have 81% efficiency. To do this, typically we're going to use a few rain gauges throughout the field to measure how much water was applied. So that's in a broad sense. If we want to do water distribution efficiency, then we need some kind of a soil moisture sensing. So we could use something like a TDR probe, and basically you make a grid pattern and walk across the field and measure that variation in soil moisture, which is also going to be affected by the soil type as you go across the field. One of the disadvantages of this type of method is basically you're measuring the water in the first 8 to 12 inches of soil surface and not necessarily deeper in the soil because of the limitations of the probes. This is the one we're going to talk about a little later on, distribution efficiency, or basically how well the water gets spread over the length of the pivot. And we'll come back to that. So what are some of the opportunities for energy or cost saving in general? We previously had talked about the irrigation scheduling, basically the water management, looking at how much water we're applying, when we're going to apply it. We can lower system pressures. Basically, it lowers our energy requirement because we're not having to pressurize or put energy into the water. Pipeline design can have some effect. Typically, this is more of a problem when we modify a system after it's been installed. We increase the water flow. Well and pump tests. Basically, we can identify problems with either the pump or the well that can affect us later on in the season. Off-peak electric use. Many utilities offer off-peak rates, so that's nights and weekends, and we'll look at how we can use that. And then there's some applications for variable speed drives, either where we have multiple fields or when we might have something like an end gun. So we'll talk more about these. So briefly on irrigation water management, what we want to do is to ensure the adequate amount of water to keep the crop from being stressed. That's assuming we're doing full irrigation. We manage it like a checkbook. An ET, or evapotranspiration, is a debit from the water budget, and rainfall and irrigation are a deposit. And we basically track that to estimate the amount of water that's in the soil. The other thing we can do is to use soil moisture sensors to check to make sure the checkbook is accurate, because our ET values, our estimated ET values are maybe plus or minus 15%, so it's not necessarily totally accurate, but it's the best we have. And typically, if we do water management, we probably can get away with 1 to 2 less applications a year, which saves us money. If you want to know more about this, we did a webinar here in February, and if you'd like, send me an email and I'll send you the link to that if you'd like to learn more about water management. I said earlier, center irrigation is the workhorse of the industry. It basically allows us to irrigate 130 acres of a 160-acre quarter-section field or more. We can do things like corner systems to actually increase that amount. And the length of a typical pivot's about 1,300 feet long if we're doing a full quarter section. And of course, they can be shorter for smaller fields as well. But that has been the workhorse of the industry. And that's what we're going to kind of focus on mostly through the rest of this talk. So the first thing is we can reduce operating pressure, but still maintain the same amount of water flow. So this example would be going from 80 psi, which would be considered a high pressure system, to 30 psi. And we can still apply the same amount of water. It's just that we're putting less pressure behind the water. And the big effect that has is the throw distance. If we have less pressure, it throws the water a shorter distance. But when we also reduce the pressure, it affects pumping characteristics. We'd have to change the nozzle package most often. And it can affect system friction losses if we allow the water flow to increase. And we'll explain why that happens sometimes. So here's based on the cost of this little chart that helps to look at or estimate the cost to apply 1 inch of water. So on the bottom here we have pumping depth. On the side we have cost per inch of water, and this is based on $4 diesel fuel. So if we're looking at 20 psi, we'd come up and hit that line and come across a little less than $1,500 per inch of water. Versus 60 psi, we're going to be about $2,000 per inch of water. So that's just kind of an estimate of showing. There's a can be a fairly good savings there, especially when that adds up over a year or over a season. So here's another example of looking at it. This is in horsepower. So if we have a high pressure system, we'd need about 104 horsepower. This is for, I think, an 800 gallon per minute flow. I think there's 100 foot pumping depth roughly. So if we can get about 7% energy savings for every 10 psi. So if we were to come from 104 down to 81, we'd save 23 horsepower or 17 kilowatts per hour of operation with that 30 psi drop. So I said it would pressure affects throw distance, and this is pictorial to kind of show that. If we have 60 psi, we can throw it with this particular nozzle. We can throw it out 48 feet. If we get it at 40 psi, it's only 44 feet. The other thing that affects is the angle of this. If we throw it up higher, we can get it out here a little further, but then wind becomes more of an issue to carry it. So it's kind of the nozzle and the trajectory of that nozzle will depend on where you're at and what you're trying to accomplish. To kind of show it a little more pictorially, some of the other things, if we can't throw the water as far, we will need nozzles at closer spacings, and that's what this is trying to show. The large circles are high pressure, and the small circles will be low pressure. Just an example. So we got the same amount of water so over a smaller area. So what that does is that increases the instantaneous application rate. It also reduces the amount of time the water is applied to a particular spot in the field. So this is an example. So how low can you go? It's going to depend on the type of nozzle you pick. So a spray or spinner can go as low as 10 to 15 psi. Impacts are typically 20 to 30 psi. You know, typically 30 psi, 20 to 30 psi is probably where most people would aim because it does affect throw distance. So this is trying to show the effect of that throw distance. So if we have a nozzle that covers 40 feet, and just depending on where it's at, oh, I know what I was trying. As we go out on the pivot, the amount of water applied increases. So this is trying to show that. So at 500 feet, we're going to cover 3 acres, and the relative water flow would be set at 1. If we go out to the end of the pivot, or close to the end, we're going to cover 7.3 acres, and that water flow is going to be 2.4 times what it would be at 500 feet to apply the same amount of water. So where we have our issue a lot of times with these is out at the end of the pivot if we increase the water flow. So here's an example of a time. So on the bottom here we have time versus application rate up the side here. So if we have a high pressure system and we look at one spot in the field out on the end of that pivot, it may be over an hour for the irrigation to pass a point, and an application rate of about 1 inch an hour. If we go to medium pressure, it increases that up to maybe 1.5 inches, 1 3/4 an hour, and our time to cover that is about almost 9/10 of an hour. If we go to low pressure, now we're up to, and this is different types of spray nozzles. So this is a low pressure spray nozzle. Now we're up to 4.5 inches an hour, and we cover that spot in 18 minutes. So quite reduced time, and this is so the less distance we cover, the higher the application rate, and the more chance of runoff, which is what we're trying to show in this. So this is our intake curve, or the rate that the soil can absorb the water. So this is for a silt loam soil. So anything that's above this, this is all potential runoff here. So if you don't have some kind of a method or a low spot to collect the water, or roughness to collect the water, it has a potential to run off. So one of the things we can do is to look at the throw distance and try to maximize that. So here we've got a spinner It can be very low pressure and actually get it out quite far. Nutator is another type, rotator. So we're best off, especially unless it's sandy soil, where you have high intakes, to look at nozzle types that'll spread that water out quite far. Impact sprinklers, they can go quite a range. The low is about 20 psi, and it depends on the type of nozzle and this trajectory angle as to how far they can control. But often impacts are used with low pressure just because it tends to spread the water a little farther out. So this graph is trying to show, this is a pump curve and trying to show the effect that reducing the water pressure has. So this point here was the design point. So it's 800 gallons a minute at 300 feet of head. If we reduce that by 30 psi or 70 feet of head, there's 2.3 psi or feet of head per psi. So we're going on 70, so we drop this down to basically 230 feet of head. And if we come over to where we intersect this line, this represents the impeller, the pump curve for a particular size impeller. If we do nothing with the pump but reduce the pressure, it's going to increase the flow rate to about 1,100 gallons per minute with this particular pump. So we need to make sure that the well can supply the water if we're going to allow that to happen. And there's some advantages doing this. But the other things I wanted to show here, this over here, this is a graph. This is called net positive suction head. That is the amount of water that needs to be above the pump inlet in order for it to not cavitate. So as we change or reduce the pressure and this flow rate increases, it actually increases the requirement for that net positive suction head. So this goes from about 10 feet of head here to probably about 18 up here. So we want to make sure we're more than 18 feet of water head when the pump is operating, so that we don't get that net positive suction head or cavitation. The green line here is brake horsepower. So we've gone here from this would be the 75 line. So about 70 horsepower to maybe a little, maybe about 78 horsepower up here. So it just shows that it does increase the horsepower slightly. The way we save money if we do this is because we've got to run less time because we're applying more water. So this graphic tries to show you. So here's the water level when the pump is not operating, and when we start operating the pump, we get this cone of depression. It's what it's called, where the water level will decrease. So we want to make sure that we have enough water above the inlet here, which is a net positive suction head, to prevent cavitation. So that's what we're trying to show there. So we have two choices if we want to go to lower pressure, because if we just lower the pressure, the pump output's going to increase. So we have two choices. One, we can pull the pump out of the well and modify it. Sometimes that means taking some stages off, and we'll talk about how a pump's put together here in a minute. But the cost of modification can be, $3,500 up. That's kind of a low ball because you got to pull the well out, or pull the pump out of the well. By doing this, we're going to lower the horsepower requirement of the pump, which will save energy in that regard. The other possibility is to allow the pump capacity to increase or go higher. We have to make sure that the well has enough capacity. So we need to do a test on the well to make sure it can supply enough water without providing cavitation. If it does provide cavitation, we may need to lower the pump in the well. But that's the first thing. Then we need to look at the soil infiltration rate. Are we going to have runoff, and how much? The other minor thing is to look at the friction loss in the pipes. is a pipe size adequate for 300 more gallons per minute without increasing the velocity head substantially. It also can affect the pumping efficiency, and I'm going to back up to the last slide here in a minute and talk about that. It does allow us, if we can pump more water, it does allow us greater possibility to use off-peak electric, which can be an advantage because it reduces the number of hours of operation. So let's back up to this graph for a minute. These green lines, this is efficiency. So every pump's going to be a little different. So you can see this one, we're kind of at the sweet point here. It's about 86% efficiency. And by moving this down, we drop down to 80%, which is still excellent as far as pumping capacity. Anything above 75% is considered good. But that's another thing that we need to look at when we change that, where that pumping rate is, because it can affect the efficiency as well. Pipe size, I talked that we can increase the velocity in the pipe. So this looks at, this is horsepower here, pipe size. So on a horsepower basis, which is the pink line, once we get above about 7.5 feet per minute, this escalates rapidly. So our horsepower requirement, once we get above 7.5 feet per minute, increases quite rapidly. So we'd like to keep that below 7.5, or possibly, usually they design it at about 5 feet per minute when you design a piping system to keep the velocity head at a reasonable amount. So how low can I go? Well, most systems can go at least to medium pressure, which will save 15 to 20%. But it depends on soil type. It depends on topography. You know, it depends on if it's rolling land. We may need to put in pressure regulators if we lower the pressure much to make sure we get even flow rate. So sandy soils, it's typically not a problem to go to low pressure. Clay soils, you probably want to keep it at high pressure. A loam soil is going to depend probably on the topography of the land. Also depends on the kind of crop cover. If we've got a perennial grass, that's a low erosion potential. If we've got row crops, that's a high potential. Now there are some things we can do to go to low pressure and still do row crops where we have a high erosion potential. So basically we use surface modification. So this one in the upper left, this is called the dammer diker. Basically it's got big paddles that make these little mini ponds in the row where it goes. So sometimes they call it basin tillage. Basically you make a little puddle that'll fill up with water and retain the water from running off the surface. This other one shows you've got a roller with it puts little impressions in the soil to help retain that water. So that's one cultural method that we can do, or agronomic method we can do to still go to low pressure, but reduce the runoff. And this is a particular problem at the end of the pivot. It's not going to be a problem near the center of the pivot. So this shows the dammer diker can hold about 3/4 of an inch of water, and there's another type that's even more aggressive as far as ditch, making a little puddle. So somewhere around an inch of water versus, say, a subsoil or a field cultivator, which just gives you a rough surface, can't hold much water. Next thing I wanted to cover is testing of pumps. There's two types of pumps out there that are typically used. One is a centrifugal pump. These are typically used on surface water sources where we have very shallow water system. And the other type is a deep well turbine pump. So the centrifugal actually, this is the pump here. It sits above the water, and it basically has to draw the water up in the inlet tube. These can be two types, non-primed and priming type. And the efficiency is lower on these, than it would be for a deep well turbine pump, where the part of the pump is actually in the water. So this is what you're seeing. This is the motor. Sometimes they're a right angle drive, and this would be the outlet for the pump, and then there's a shaft that extends down into the well. So that's what we're trying to show here. So here's our drive unit, whatever type, and this is our stages for our pump. These pumps are typically made up of a series of stages that pressurize the water in sequence to move it. When they make a irrigation well, they typically bore this out. They put a casing in, which is this, and then they backfill around that casing with a gravel pack. And basically this is to try to prevent the fines in the soil from plugging up this screen, and basically you don't want to pump sand, essentially. So that's kind of the way. So when we have to modify a pump, we have to pull this whole thing out of the well, and we typically are either changing the size of the impeller, or maybe we reduce the number of stages on the pump, depending on what the requirements are. So on pump testing, there's been a number of studies throughout the years on testing. Every time they test, they find that our pumps aren't as efficient as basically Nebraska does lots of irrigation. They came up with a pumping criteria, Nebraska pumping criteria, pumping performance criteria. And every time we do one of these tests, we find that basically here we had an average of 25% less than the criteria in Wisconsin in '85. Here's Kansas in '93. Found more than 40% more fuel was used than if needed, and even in Kansas, where they do lots of study, they found that 15% of the pumps exceeded it, but the average was 77% of the pumping criteria. But what's interesting, by doing this test, they found where the problems were, and then they could correct them. And they found that 57% of them could be improved by just an adjustment, either the pump or the engine or both, which increased the efficiency an average of 14%. So one of the things this pump test does is it identifies where you have a problem. Whether you're going to fix it, then once you know the problem, then you can determine whether it's economical to fix it and how to fix it. One of the ways we can look at our pumping efficiency, there's a publication that Kansas State did evaluating pumping plant efficiency using our energy bills. And basically here's the information you need, and if you go through that publication, you can estimate what the efficiency of your system is without actually having to complete the pumping test. And at least it gives you a ballpark to see if you should spend the money for a pumping test, although it isn't very expensive. To do a pumping test, basically we're going to determine whether the well and the pump meet the design specifications or when it was put in. Basically, gallons per minute at some total head, and whether the well can supply the water. That's another thing. We may have a pump that can pump fast, but if the water can't flow into the well fast enough, then that could be an issue that we need to relook at how the well, or do some work on the well casing itself. Sometimes you get fines up against the screen. And they can sometimes actually what they do is they put explosive charge down in the well and try to blow the fines back away from the screen in some cases. The other thing you do is you look at drawdown, make sure that we meet our net positive suction head pressure, and we can record the energy use during this test and calculate the energy efficiency and compare it to the pump curves to see where we're sitting. Ideally, we should do this test every 2 to 3 years, and it's not real expensive. I look at it as cheap insurance because pumps never quit when they're not needed. So I think it's a good expenditure of money every couple of years to make sure, especially if you're doing lots of irrigation. Some of the pumping problems we can have excessive clearance between the impeller and the housing, or worn seals, and we're going to show what that looks like here in a minute. Lower water tables can have an effect on especially the net positive suction pressure, or plug screens. Motors or engines, they either need some repair or maintenance, or sometimes they're improperly sized. Example of that is we may have had a motor, maybe we got a 125 horsepower motor. We changed to a low pressure system, but we didn't change the motor, so now it's running only 50% of capacity. Well, larger motors aren't necessarily, their efficiency drops rapidly when we get below 50%. So it could be that we need to replace the motor. Gear head maintenance, changing oil, make sure the gears are properly lubricated and that they're matched correctly, that for the engine and the pump to work together properly. And then sometimes the pump is just the wrong pump for how it's being operated today. If we get out of that sweet spot for the efficiency. So here's an example of a pump seal. So this is looking at a stage. So this would be one section of a pump. This is the impeller that spins around. The rest of this is stationary. So the water's moving up through here, and we have this seal right here. And what happens is sometimes this will wear, and when it wears, all of a sudden we get this big gap here, and so the water will come back around. So you get leakage. We're spending the energy to pressurize it, but then it's leaking around. So that reduces the efficiency. So sometimes it's just a matter of this shaft can be adjusted from the surface, and sometimes it's just a matter of moving this down a little bit so we can get that, reduce that clearance there, and we can improve the pumping efficiency, at least for a while. It may be short term, but at least for a while. At some point you need to pull it out. So what is the pumping plant criteria? Basically, it depends on the type of fuel use we're using for it. But this is this third column over here. This is the water horsepower. So this is the amount of energy that we're actually adding to the water. So this is in water horsepower. And this is the amount of horsepower we'd need to generate from our engine, the output of the engine, to supply this amount of horsepower into the water horsepower. So it's going to depend on the type of fuel that's being used. Now the overall efficiency is quite different. Electricity, an electric motor of large size, about 90% efficiency, versus a diesel engine is only 30 to 35% efficiency. And then we have the efficiency of the pump itself. If we base it on the Nebraska pumping criteria, that's about 75%. So, if you took 90 or 75% times 0.3, you're going to get right in the middle of this, about 22%. So that's the theoretical maximum you can get. Here's what the recommendation is. If you test one and this is what it runs into, 18%, then you probably leave it. But you can get lower values, and these are the average of what we come from field tests. So there's always seems to be room for improvement. Most of the time, it's whether it's economical. We're going to save enough energy to pay for the cost of modifying the pump. Variable speed controls on well pumps have been, because of the cost of the variable speed drives have come down, this has become more cost effective. But basically we can regulate the pump speed to maintain a pressure. We can either do this manually or automatically. So if we did it automatically, we'd actually have a pressure transducer that would speed up and slow down the pump to run at a maximum or a set pressure. So a place where you might use one of that is if you had end guns or corner systems that were causing trouble, because when an end gun comes on and off, it it will affect the pressure of the main line of the system and affect the flow rate out. The corner system will do the same thing. So we could use a variable speed pump to maintain that pressure to make sure we always have 80 psi or whatever that system is running at on the system. The other place we can use it is if we have multiple center pivots running off of one well. So I'm going to show you an example of that. So here's an example. We've got center pivot A is right near, here's the pump here. So center pivot A is right near the pump. Center pivot B is 2,000 feet away. Well, we're going to have 2.5 psi loss between the pump and center pivot A with 50 feet of travel. With 2,000 feet, we lose 30 psi. So if this pump can only run at one speed, then center pivot B is going to run at 50 psi, and center pivot A will run at 7 to 7.5 with an 80 psi at the pump. Well, if we put a variable speed drive in here, we might still run pivot B at 50, but now we can run pivot A at 50 by just adjusting the speed that the pump runs at. So it will affect the efficiency of the pump, but because we're reducing the pressure, we probably will save energy overall. So here's an example of spoking, or things that can be caused by end guns coming on and off, and these are dark lines that you see coming out. So dark lines are where you got adequate water flow. The white lines are where you probably didn't get enough water. So that's an example of what we call spoking. So this is affected by changes in water pressure or sometimes slippage of the wheels of the center pivot itself. So the next thing I want to talk about is uniformity testing, and basically to see if we're applying water evenly across the field. One of the problems I have is, or not a problem I have, but you know, with automation today, people can start and stop these things without ever going out to the field to look at them, or they'll sit in their pickup truck and look at them. And well, there's water coming out, so you're assuming it's being applied evenly. What this test looks for is the amount of water applied to the soil, not what's in the soil, moisture, and that's just because of the cost of doing it the other way. So indirectly, it's going to check for sprinkler wear, restrictions, and rotations. And we can also use it as a commissioning test if we put new sprinklers on a system to make sure they're put in the right order. Because it happens. People open the wrong box and the wrong section and get them in the wrong order. The recommendation is do this test every 3 to 5 years, and sooner if it's used a lot more. And to do this, you need a lot of rain gauges, as you saw from the previous picture. And what we're trying to look at is the sprinklers themselves. Basically, they don't last forever, about 10 to 15 years, depending on the amount of use. So, the obvious problems you can see from a pickup truck. So here's this one's a check valve that didn't close. Here's a nozzle that's not spinning properly. It's plugged on one side. Those are the obvious problems you can see. What this test is going to find is the not so obvious problems. The spinner it's going around, but it's not going around the right speed. The other thing we can identify, and this would be on a commissioning type test. This is an example of here's one nozzle here and one nozzle there. They're probably either not the right nozzle or the pressure's been reduced because we're getting water deficit in between the nozzles. So it's an example of that they're not, it's not designed right, or there's been a change in the system. So that's the kind of problem that it'll do. Here's an example of a plug nozzle. So you get this little valley underneath. What this test won't do, it won't necessarily pick up spoking that I talked about earlier because of the way we're going to test. But it does it looks for over or under watering. We can identify areas where we've got too much water that can cause plant diseases. And what's important, if we're doing chemigation and we don't if we have uneven application, that affects our fertilizer, herbicides, pesticides, whatever we're doing. And if we got an area that's putting on too much water, we can get localized leaching. So we're trying to identify those areas. We look at the cost of poor uniformity. So I'm using a 40-foot diameter nozzle span. I looked at potatoes. So if I get 20% less yield, and my excuse me, my average yields were 350. My selling price is $5 a hundredweight. Depending on where that product nozzle is on the system, can affect my loss basically from lost sales. So when you get up toward the end, that can almost pay for a nozzle package. So what we're trying to do is identify problems. So uniformity, nozzle maintenance, poor water quality can have an effect. We get iron in the water or something that, or high minerals that cause deposits on the nozzles and cause them not to function properly. I already talked about variations in end guns and in corner systems, wheel slippage, and wind. Well, we can't control wind, but we can control the type of nozzle to help us fight against wind. So what we're trying to do is measure the amount of water that comes out of the nozzle. So there is actually a standard out there. American Society of Agricultural and Biological Engineers have a standard. The standard recommends 2 lines of rain gauges for this test. And if you did that, you might catch spoking a little bit, but it depends where it's at. Typically, when we do these tests, we're using 1 line of gauges. 1, because it takes so many gauges, and if we want to have 2 measurements, we can run it forward and then run it backwards over the line to get this testing done. So what this requirement does, we have a row of gauges. Depending on the type of nozzles is the distance we put these gauges apart. Basically what we want to do is we're spacing at 80% of the nozzle spacing, because we don't want them in the same spot between the nozzles all the way up to the lateral or up the pivot. So we're going to space them out differently and catch the water and measure it. We look at end guns. Typically the requirement is that 75% of the wetted radius should have even water distribution on it. So if we've got one that's 80 feet wetted area, we're only going to look at calculations of 60 feet in our calculations, or expect that area will have uniform water distribution on it. These kits can be very simple. Here's one one we use here in Wisconsin. It's just got some soda cups. We've got some stands we've made up, and some other for measuring and recording the amount of water. Everything in a couple tote boxes. This kit I showed you earlier. This is these type here down in Kansas they use. These are nice. These are actually excellent rain gauges too. One, it's got a bottle that you can read off until they get rubbed off. Has a big opening. You can put these out in the field. They have a small opening between the bottle and the collector, so they have very low evaporation rates. So you can put them out and come back a couple days later, and they still be fairly accurate readings. So there's an example. The one we use costs about $2 a piece to put them together without labor. So here's the kind of data you can get out of this. So here's one. We've got these are the collections across a pivot, and you can see this is trending down. That's what the red line is. But here's the average. This is 10% above the average, 10% below the average. That's what these dotted lines are here. And that's where we'd like all the readings to be. If we were in that range, we'd be above 90% with what we call the coefficient of uniformity. This system here is 72. So that's considered poor. Anything below 75 or right around 70 is considered poor. 85 is good. Above 90 is excellent. So we want to get up into that range. So The next one here, this one was at 90%, and even though it's got a couple spikes here, it's not as high because you have to look at how this range is set up on here. But you can see most of the readings fall within this plus or minus 10% on this range. So, and this here might be one spot. It could be splashing off a tower. It could be a rubber boot that's got a leak. We can also do this type of testing on solid set systems or hand move systems. In this case, we can't look at the whole length of the system, but we can look at an area. So we'd select an area on our center pivot or our solid set system, and we'd set rows of catch cans out there to catch the water to measure it. The uniformity on a solid system is not quite as not expected to be quite as high. I think it's off the top of my head saying it's 70 or 80% would be an excellent system. Just you don't have the overlap, and it depends on the type of nozzle you're using. But it can be done on those types of systems as well. We can also do it on a traveling gun. Here we've got a row of gauges across the field, perpendicular to the travel of the big gun or traveling gun. We let that come past the gauges, and then we can look at the water. So here's a chart of what that would look like. So this is actually fairly uniform through this area, and we've just got this one area over here. So I think this is the side it goes and turns back. So this could be just a simple maintenance thing that we could look at to improve the efficiency of. But now we've got some data that we can actually look at and see if we can make an improvement on that particular piece of equipment. Off-peak electric, although not saving energy per se, it can save us money. So here's an example. This is Liant Energy, is a local utility here in Wisconsin. So their general rate is about 12 cents a kilowatt hour, but they have off-peak electric rates of about 5.5 cents. But if you do that, you're going to pay 21 cents if you're on peak. So to take advantage of this, you basically have to be able to irrigate in less than about 100 hours a week. Basically, weeknights and weekends are off-peak. This type of system, to do this, you're going to need about 1,200 gallons a minute on a quarter system or a quarter section pivot, straight pivot, and about 1,400 on a corner system. And that's for here in Wisconsin. If you're in Nebraska, you're going to need higher flow rate than that probably. It's basically only useful on deep-rooted crops. If you get something like vegetable crops that are shallow-rooted, like potatoes, you're in the heat of the summer, you're going to end up needing to water on peak quite a bit in order to keep that plant from going into stress and reducing the quality of the crop. But for things like corn and soybeans or deep-rooted crops, no problem of doing that. So here's an example of the savings you can have on a system. So here's my general purpose rates, about $8,900. This was for a year. This is based on 11 inches of water. So the next one is $6,200 when I had to use 20% on peak. Maybe I had a couple hot spells where I had to water on peak, and then $4,000 off peak. So I can save, basically 50% if I can do it all off peak. So that's a substantial savings. The other thing to look at is fuel switching. Diesel fuel at about $4 a gallon. The equivalent energy would be 28 cents a kilowatt hour for electric. Well, we're typically spending only about 12 cents. So we can reduce our cost of irrigation by about half if we go to electric from a diesel. One of the issues is it available and what's the cost of installing it? And whether your utility has enough capacity to power you. That would be something else. Natural gas would be the other one. It would be about half the price, typically, because we're about $1 a therm now. or 70 cents a therm in some cases. Whereas LP gas, that would be probably about a swap depending on the time of year, and gasoline would be more expensive. If we're looking at energy conservation, there are some grant programs. Anytime we can save energy, the utilities, or especially for your have an electrical powered pump, you can contact your local utility to see what grants are available. Sometimes the state energy office can tell you. There's also a website. This is the state database of state incentives for renewable and efficiency. This is a website. So they have both state and federal incentives on that. And the incentives can be either direct grants or incentives. Sometimes they're production, so so much an hour, or for renewable energy, it's so much energy unit produced. Or sometimes they're tax incentives. Right now there's a 30% tax incentive for some types of efficiency or renewable energy. There's also the REAP program, or Rural Energy for America program. This was in the 2008 Farm Bill. Although with sequester in the last couple of years, this has been greatly reduced. At one time it was $100 million a year. Now I think last year it was $20 million, which is a drop in the bucket for the number of projects that come through. But it's another source of funding, and they either have grants or guaranteed loans at low rates. So that's another program. There's a couple websites that have more information on those programs. The NCRS EQIP program also has some programs depending on your state and location. There's one looking at sprinkler systems, basically doing a uniformity testing and looking at uniformity. And then there's a water management one as well. So these typically are so much an acre, irrigated acre, to do these tests or management change. Here's some reference material you may find handy. This sprinkler irrigation book has been around for a while. It's still very good. It would cover some of the testing we were talking about. Kansas has a nice site. Here's Nebraska down here. In Wisconsin and many states, they have sites to get those ET numbers. So there's ET values, estimated values. So there's our site. You can contact your extension agent for where the sites are in your particular area. The NRCS also has some irrigation handbooks, references. And as of the first of the year, we've got a online curriculum, much of the material I covered here today, plus some. We have an irrigation unit, which I've given you a link to here, that has basically an online thing that goes through what I've talked about today, plus some. So you may find that handy. So with that, we'll bring this to an end and take any questions that people may have.